Now on to asymptotes. Every reciprocal function has potential to have both a vertical and a horizontal asymptote. The parent function has asymptotes, as we saw on the first screen, at 0 for x and 0 for y. The vertical asymptote, if you need a reminder, for any reciprocal function, the reciprocal function kind of presents itself as one function divided by another function. When you're trying to find the vertical asymptote, really you need to narrow in and focus on that denominator. Don't ignore the numerator for the possibility of wholes, but whenever this denominator is 0, those values of x become or are your vertical asymptotes, because then the function will be undefined. You're trying to divide by 0, and that is not something that is realistically possible. Those are the values of x that give us the vertical asymptote. We've done that before. Here's the brand new exciting thing, horizontal asymptotes. Now keep in mind not every function will have a horizontal asymptote, but if it does, what we're doing is we're expressing the end behavior of that function. We are looking at what happens with the outputs as the inputs, or x, become very large. Analytically, what we're going to do is see what happens as x approaches infinity. Now mind you, you cannot substitute infinity for x. You can't plug in infinity and say infinity plus 1 divided by infinity minus 3. That's hard for the human mind to wrap around. So what we're doing is we're actually calculating a limit as x approaches infinity for our function. And if that function equals some number at infinity, then we have found the horizontal asymptote. Now, the how-to on this, maybe this would be a note worth writing down because Mrs. D didn't type it in here. How are you going to do this limit calculation? This special limit calculation will require you to divide every single component of each function in the numerator and the denominator by the highest power of x. And that's the highest power of x within the entire function. Numerator and denominator both considered. Okay, we'll see how that works out on the next slide here. Here we are. We will find these functions' asymptotes. We'll start with the vertical asymptote because that should be familiar territory. In the function f of x, we will focus on the denominator function, x squared plus 3. Whenever that equals 0, the function is undefined, and therefore we have an asymptote, a vertical asymptote. As I start solving here, I'm starting to get a little nervous about what happens right about now. We have an imaginary value for x, which tells me there are no vertical asymptotes in this function. And that's okay, we can handle that. I kind of planned that. How about the horizontal asymptote? Here we're going to take the function and we're going to evaluate the limit as x approaches infinity. Now don't freak out about the new term limit or even this notation. We're just trying to see what happens when x is very, very, very large. Recall that it's very difficult to say 2 times infinity divided by an infinity squared plus 3. You can't tell me what that equals. It's a little easier to manipulate and understand very large numbers like infinity when they are in fraction form. So that's the reason we're dividing. We're going to take 2x, and I notice that the highest power of x in this entire function is x squared. I'm going to divide it by x squared. Do that with every piece of the function. So x squared will also be divided by x squared. The positive 3 will be divided by x squared. Before I evaluate the limit, I'm going to rewrite it one more time by simplifying a little bit. 2x over x squared more simply is 2 over x. And if I just pause and think about that for a moment, 2 divided by a very, very, very large number, maybe take 2 divided by a million, bazillion, gajillion. That's going to be a really, really, really small number, like 0.000000000000002. That basically is approaching 0. We'll see what happens in our denominator with each of these terms. X squared divided by x squared more simply is 1. Even when x is very large, million, bazillion, gajillion, that number is still 1, unaffected by a variable. The fraction 3 over x squared, now we're taking 3 divided by a million, bajillion, gazillion squared. That's going to be even smaller than the numerator, but also approaches 0. So I have not said that 2 divided by infinity equals 0, but it's approaching 0. It's very close to 0. Likewise, that 1 is approaching 1, 3 over x squared is approaching 0. And if I evaluate here, I basically have 0 divided by 1, which is 0. To me, that says that y is approaching 0. This is your horizontal asymptote. The y values, the outputs of the function, approach 0. Next, function. This is a good one. I don't think this one will have vertical asymptotes either, but I could make it. Let's make it. Let's just have a little fun with this. We're going to turn that into a minus 8. So for the vertical asymptotes, we'll look at what makes that 0. Yep, now we're going to have some asymptotes. I can say 2x squared then equals 8. By adding 8, I can say x squared equals 4 by dividing by 2. And I can determine 2 asymptotes, actually, at positive and negative 2. We have vertical asymptotes at x equals 2 and at x equals negative 2. It would probably be safer to write that as 2 separate equations to remember for your own sake when you try to start graphing these functions that there are 2 vertical asymptotes, not just one. I'm going to need a little more room for the horizontal asymptote. Here we are. We're going to evaluate our limit as x approaches infinity for this function. Once again, the highest power in the numerator and denominator is x squared. So every single term is going to be divided by that x squared. We're kind of bringing it down to smaller, more manageable terms by doing this. And I just know how much you guys like fractions. Even that 8 gets divided by x squared. Now, watch and pay attention. This one works out a little differently. As x approaches infinity, if I simplify, x squared divided by x squared is 1. I have 2 over x. Again, I have negative 3 over x squared. Again. And the denominator is a 2 minus 8 over x squared. Now imagine if x were very, very large. Regardless, this 1, no matter how large or small x is, that will still be 1. 2 divided by a very, very large number, like a million. I don't have to say bajillion, gajillion. Those aren't even words. 2 divided by a very large number like a million would approach 0. 3 divided by that very large number squared is also 0. Very, very small, even smaller than the 2 over x quantity. Regardless of the value of x, the constant 2 will still be 2. And 8 divided by a large, large number squared is very, very small, approaching 0. Here we have a value. We have 1 divided by 2, which says the y values approach 1/2. This is your horizontal asymptote for this function. Y is approaching 1/2. In summary, as x approaches infinity, what we are determining is your horizontal asymptote, the end behavior of the graph, can be determined not by plugging in infinity, but approaching there using a limit calculation. Okay? This is the way that we determine the horizontal asymptote. Okay? As x approaches an undefined value, I gave some room here to draw a little picture. So here's an undefined value. As x approaches that undefined value, let's pretend it's 4. What the function will do on either sides of that asymptote, and maybe you noticed this before, as x approaches that value of 4, I'll come here from the right, the function is approaching infinity. Now don't let that confuse you with the input approaching infinity. This is not the end of the graph. This is somewhere in the middle of the graph, we'll say. The function is shooting up to infinity at that vertical asymptote. This is your infinite discontinuity, remember. Also, on the other side of the asymptote, the vertical asymptote, this is what I've just drawn. As I approach from the other side, the function is approaching negative infinity. Another reason, confounding reason, that we have an infinite discontinuity. That undefined value, or the vertical asymptote, causes the function to dive down, in this case, to a negative infinity on the left side of 4. Last summarizing point is that intercepts all possess 0 for one of their coordinates. If the input is 0, the output is what we call our y-intercept. And if the output is 0, the input is what we call our x-intercept. These are special points. Recall the coordinate form of them, 0y for the y-intercept, x 0 for the x-intercept. The second point isn't super important to you at this moment, but when we try to piece together all of this information and create a graph, that will become pertinent information for you. I hope that you've learned about asymptotes and intercepts and can be successful in your practice. Keep learning. Signing off, Mrs. D.